start, I think. So last week, I had primarily given, hi Sangeet. Okay, maybe let's wait a couple more minutes. Yeah, I apologize for the little bit background noise, and yeah, I'm not in my hostel now. Mhm. Okay, so let's start. So let me first take you back to week 0 and 1. So in week zero, which was kind of more of a prerequisite, we had discussed probability. So this is kind of a prerequisite, but it's always good to have a refresher. So we discussed a bit about discrete time and continuous time probability. And then we started with queuing theory. So this was just kind of a brief introduction into the field, and also some of the initial notations, for example, the Kendall's notation, and subsequently certain fundamental properties of queues, some discussion on that, and the fundamental theorem, which is Little's law, which governs all general queues, whether or not they follow the Poisson distributions of arrivals and departures. It doesn't matter. Any queue of whichever application has to follow Little's law in steady state. So, and some discussions on some initial problems. Now, from week 2 onwards, we will actually start polishing the tools that we need in order to analyze queuing systems. So, and as always, we start with probability. And the fundamental topic of this week's discussion is essentially stochastic processes and how we eventually study Markov chains. So that is really the cornerstone of this lecture. So the goal is really to first learn stochastic processes and various properties of stochastic processes, and then of course the Markovian property, and then use those notions to characterize Markov chains and study various properties of Markov chains. So yeah, so I'll start. So before going to Markov chains, can somebody fill me in on what do, because this is basic probability again, what do I mean by stochastic processes, or another name is random processes? Can somebody chime in on this? Any basic idea, anything? Like, you don't have to be very mathematically rigorous. I myself am an engineer by training, so I'm not rigorous, but yeah.
A sequence of random variables.
Yes, exactly. Yeah, so very concise way of expressing, it's a sequence of random variables. So we had studied a bit about random variables earlier. And so essentially, if we have something like x of t, t obviously denotes time. And at any time t, for all t, so essentially x of t is a random variable for all t. So so we have some kind of set like omega, and there is a field f and p, so the standard probability notation, and the probability function maps from the set omega to, as we know, 0, 1, right? So this is a probability function that defines a random variable really. And on top of it, so let's say if the set is called omega, we'll call the variable small omega. And on top of it, we have another variable, which is time, because now this process, this kind of, so again, like if I draw x of t out, so this won't be just a single curve. Instead, it will be kind of an assembly of various kinds of curves with, so let's say each of these curves have their own probability. Let's say for simplicity, we have two curves with probability half. So at any time t, with half probability, the process will behave as the curve below. With half probability, process will behave as the curve above. So then x, this quantity x essentially becomes a function of, let's say, t and omega, because it's varying with time, and again it is also a random realization of a certain number of possibilities. So there are two variables here. This is how we will denote a random process. A random process. So, and why are we studying random processes? It is because random processes are key to model any kind of like queuing system in general. So because in any queuing system, there are like there is a lot of randomness involved, and the system evolves over time. So both of the topics come into the picture, and so eventually then we move on to study various kinds of processes, right? So let's jump to that in a bit. So most importantly, so till this point, is it clear, or do you have any doubts? Because you should understand what a random process is before we move further. If you have any doubts, you can obviously ask. So the most important property that we should learn. So let's start with some simple properties. So, okay, so properties start.
So I have just one
Yeah,
question.
yeah,
So when we say that we take one realization of omega and we
yeah,
see the time index of the random process, right?
yeah.
So that omega should be like where does that omega lies in? Is it like I mean,
Um,
you understand, right? For example, if we
hmm,
are like tossing a coin
right.
like infinitely number of times, and we want to see just one path of that stochastic process, so we should give the input as omega, the
But
all
that's
the info.
the yeah, that's the whole point, right? It's not in your control. It's not so it's not a deterministic. Then what you are describing is a function x. Like I get your doubt. So here there are two functions. Let's say x1 of t and x2 of t.
Yeah,
Now if it was predetermined, then we wouldn't have any randomness here, right? So if at any time t we knew exactly how this phenomenon, whatever we are studying, will look like, will behave, then there is no randomness, right? Then we will know that it behaves as x1 of t, it behaves as x2 of t. Even even let's say if you form a rule like it will behave as x1 of t in a certain range, a1 to b1, and it will behave for a certain range of time, let's say certain range of time, and x2 of t for a certain range of time, let's say b1, like let's me just so something like x1 of t from minus infinity to b1 and x2 of t from b1 to infinity. Like let's say if this is again this is t, let's say if this is known that this is the behavior, even then this is not a random process really, this is again this is deterministic, right? Because we know for sure what the value will be. Is that clear? Like
yeah, yeah,
if the whole point of a random process is we don't know for sure, it's random. So all we can do is we can calculate statistical properties, and this will be the expectation, this will be the variance, this will be the mean, and like all of those statistical properties, but it's not deterministic, so we don't know for sure. Okay.
okay,
Yeah.
got it.
So again, yeah, so coming back to the properties, so the most important properties that we need to study are firstly, like we so this is more like a classification of random processes. So first is independent, right? That any like x of t1 and x of t2 have no, like, are independent essentially. So that is the idea of independence, that no two the process happening at no two time at no two time instance are the processes really dependent on each other. So it's like there is no temporal dependence here, like at any time you have the same kind of a dice. So using that analogy. And the second most important property is stationarity. Stationarity. So there are two kinds of stationarity here. So and I think this is like well known among people in the communications and signal processing field. Like I come from the same field. So there is strict sense stationarity, strict sense, and there is a wide sense stationarity, right? So by strict sense stationarity, what do we mean? That the, let's say, a joint distribution of like xt1 t2 xt2 tn, actually, like, let me put it this way: t1 plus c1, and similarly till xt1 plus cn. So this doesn't, let me, yeah, use space better. This doesn't depend on t1. So all that matters is the difference in the time indices. If the difference in the time indices are the same, the I mean the starting time of this sequence of times, let's say t1, doesn't matter. It's just that the difference has to be the same. It doesn't matter in a very strict sense, in the sense that the joint PDF itself has to be the same. But a more popular and a more practical approach is wide sense stationarity, where all you need is that your mean of the random process x of t, the expectation should be independent of time, and the covariance or correlation actually x of t minus tau, this should be always a function of the time difference, right? Which is known as the autocorrelation function. So these are the wide sense stationarity properties, and for us and in general, this will be the more important property because this is more practical. This is how more practical systems are modeled. We assume that the time difference is the only factor in determining the correlation between the random processes at two different times, and also the mean, no matter what the time instant is, the mean remains the same, right? Is this clear, more or less? And another, so these are kind of two. Sorry, yeah, please continue.
Yeah. So that means in the stationary side, I mean, it's going to be the mean and variance is going to be same for all the time, but whereas in wide sense, the covariance, it depends on your time difference. Is this understanding correct?
So in wide sense, we'll just have these restrictions on the mean. So the mean has to be constant, independent of time, and the correlation has to depend only on the time difference. So we really don't care what is the value of t here. It will depend only on the time difference, which is tau, let's say. So yeah, but we don't have any conditions on, let's say, something like expectation of x of t1, x of t2, x of t3. We don't have any conditions on this. Like it can be anything. But at least till the second degree, we have wide sense stationarity, and so I'm just using short forms here. So this is strict sense is, let's say, SSS, sorry, doesn't, and this is WSS. And also note that strict sense station, you can prove it. This is not a probability class, I'm just kind of skipping this. The strict sense stationarity implies weak sense or wide sense stationarity. So if the first holds, second automatically holds, but wide sense stationarity is more general, so the reverse is not true. So this is not true. Is that clear? Okay. So now let's move to another important kind of processes, which is stationary independent increments, right? What do we mean by that? So we'll particularly study we'll study some examples actually, and I can, for the sake of time, just but I should state the property first. So let's say you have a random process x of t. So you record it at a time t1, and you record it again at a time x of t1 plus h. So it can be anything. Let's say the weather, the temperature. So what you're trying to measure is x of t1 plus h minus x of t1, right? So what you so you're trying to measure how much increment has happened in the time interval h. So you want to check if this value, this increment, depends only on h. So if this depends only on h and not on t1 by implication, so this increment depends only on the the time interval. In that case, we will call this stationary increments. Is that clear? So So it's not, so it's only dependent on the time interval. The difference in value is only dependent on the time interval and not the exact time. So an example of a case where this will hold true is obviously time itself, or like, yeah, some or like packet flows in networks and stuff. And maybe the weather is not a good example because the temperature difference between two times can be very different depending on what time of day you're measuring it. So, but one important process that follows this kind of a, and also it should be, and by independent increments, we mean that, let's say x of t2 minus x of t1 and some x of t4 minus x of t3, these should be independent of each other, of other. So it shouldn't matter, like the values of t4 and t3 shouldn't impact the values of t2 and t1. Like both of these are kind of independent. So that is independent increments. So is this clear? And one important phenomenon, like two phenomena actually. So Poisson process is used for modeling queues. This follows both stationary and independent increments. This is primarily what is used to model queues. So I'm kind of putting a double line, and the other one is Brownian motion, which you might have heard in physics, and is also used to model other things like random walks and things like that. So so is this clear? And then actually, like from here I'll jump to a problem which directly utilizes this, like the property of, yeah, this property of difference, and like that will help. But yeah, any questions firstly? Okay. Okay, so let's discuss a short problem. Brownian motion in Wiener processes. So the random process describing the Brownian motion is known as a Wiener process. It's named after a scientist. And so this is discussed in the lecture. So this has all of the properties mentioned above. So it actually, the difference Wt plus u minus Wt, this is actually in Wiener process, it is distributed as a normal, like normal distribution with mean 0, and the variance is always u, which is the time difference. So it fulfills the criteria here. It fulfills independent increments firstly, and it also fulfills, and it has Gaussian increments, and it only depends on u. So it is stationary increments. Is that clear? So, and also the another property, this is first. Second property is the value at 0 is 0. So this is known deterministically. And then third is Wt is continuous, and 4 is, and then it's like less of a it's more of a corollary. So from 1 you can imply this, that if you set t equal to 0, then and you know that, so set t equal to 0, you know that W0 is 0. So what you will have is WU is normally distributed, and t equal to 0 normally distributed as 0, u. So at any time u, or let's say if you set t equal to 0 and u equal to t, then Wt at any time t is a function of the time. And what kind of function? This is a PDF. We know how the Gaussian PDF looks like. This, right? So this will be f x of t, let's say x for x greater than 0. Is this clear?
One question.
Sorry. It will be t greater than 0, not x greater than 0. Yes, please.
So do we really need the continuity assumption, or like, I'm not sure, or
Yes, I mean, you can check directly from the formula itself, right? This is a continuous distribution. Like it's an assumption, and like this is used to model. We actually need it
okay.
because realistically, real quantities. The reason this kind of axiom has been taken is this kind of property actually models real processes, like the Brownian motion, for example. So we do use these kind of distributions to model. Let's say I come from a wireless communications background, so we use Brownian motion Wiener processes to model blockages in millimeter wave networks and stuff. So it's kind of practically used as well. So let's do a small problem. Let's say now let's say you are given that WT t greater or equal to 0 is Brownian motion, right? So then you have to compute covariance of some WA, WB. So how will you calculate that, right? So any idea? So covariance, again, the formula just from like memory is expectation of WA, WB minus expectation of WA, expectation of WB, right? This is from probability statistics. This is how covariance is defined. And one important thing is that like WT, as we kind of obtained that WT for any time t is distributed as normal 0, t. So the mean is 0 always. So that means these two quantities go to 0, right? So all we are left with is expectation of WA, WB, so which is the same as the correlation. So this happens when the mean is 0, that the covariance and the autocorrelation are the same. And so another kind of mathematical jugglery that we can do is express WB as WA plus WB minus WA, right? So then, if you break things up, you will have expectation of WA square, and you add expectation of WA times WB minus WA, right? Okay. So I hope this is kind of clear. Right? And so we know, so now two things here. We know that from this property, the variance of WT is T, so this will come out to be A. And the second term is, so again, this is a bit of a jugglery. We know the independence property that this follows independent increments. So WA is nothing but WA minus W0. W0 is equal to 0. And this is WB minus WA. So these are independent increments, right? And so they will have no correlation. This is, after all, the correlation between two independent increments. Independent processes are uncorrelated, right? Independent processes are uncorrelated, so we can just ignore. This will go to 0. So A plus 0, this will come out to be A. It's kind of a nifty result on Brownian motion and Markov processes, and like this comes in handy. Is this clear? Or I can repeat.
Yeah, it's okay, but actually, like in the current lecture, I think we haven't covered this thing in Brownian motion. I think we haven't covered till week 3.
Yeah, so this I'm mostly covering week 2 because like it's not possible for me. So like the first class, the first lecture that I took was the kind of tutorial session I took was last week, in which I could only finish week 0 and week 1, and it's kind of not possible to finish more than 1 week in one tutorial session because then it will be just too much of content. Firstly, too much of content to kind of deliver an effective kind of guidance thing, and also it will be hectic to prepare as well. So in just case, I know this was basic, but I thought I'll just kind of touch upon it. But
This was not. I think this was not discussed in the tutorial actually. It is.
yeah,
I
this
think
wasn't discussed.
the
This
professor.
wasn't this. Yeah, this wasn't discussed in the previous one because we hadn't talked much about stochastic processes yet. We are just
No, in the
anyway.
NPTEL lecture till now,
Hmm.
I think the professor haven't taught us this Brownian motion of Wiener process till now, or I mean, he
Yeah, no,
hasn't.
it is there in week 2. I
Week
myself
2.
reviewed the lectures in week
Okay.
2.
Okay.
The very first lecture 5, concept lecture
Stochastic
5.
process, review of stochastic processes.
Yes. So
Okay.
that is what I'm starting with. So this is
Okay.
the Brownian motion is a very important example of a stochastic process. And now what we'll jump to Qs. So we'll jump to the primary property of queuing processes, like queue processes, which is Markov processes. So all queues are modeled as Markov processes. And yeah, so let's say, so by Markov processes, the key property of Markov processes is that the distribution, let's say f of x of t plus 1, like actually we should write it in discrete time notation, n plus 1, f of x of n plus 1 given xn minus 1 till x0, let's say x0, sorry, this is equal to x of n plus 1 given xn. So this is the like in a very simplistic term, this is very fundamental characteristic of any Markov process, that like given the entire past history of the entire past history of a variable of a random process, the only pertinent value is what has happened just before the current moment, and it doesn't depend on what has happened earlier, right? So this is kind of the key idea of a Markov process. Is this clear?
Yes.
Yeah. So if this is clear, then let's actually break this down a little more. So let's say let's give it these values. So x of n plus 1 is, let's say, small x plus 1. This is xn. This is xn minus 1. Minus 1. This is x naught. Right? So if we use the probability theorems, then we can write it as x of n plus, let's say we want to find the joint distribution of xn plus 1, xn minus, let's write it as xn x minus 1 going all the way to x naught. We want to find this joint distribution function. So we'll start taking conditionals, right? This is again basic probability, x minus 1, x of n minus 2 till x naught, and this sounds familiar. It's just known as a total probability theorem or something. Yeah. And then we know this is a Markov process, right? So yeah, just write it down again. This is Markov. And Markov means this property holds. So then this will become f of xn given xn minus 1 because it doesn't depend on anything else. Similarly, this term will become f of xn minus 1 given xn minus 2 times f of f of xn minus 2 x naught. So this breaks down using the same total probability theorem. It breaks down to this. And so on and so forth. So what you'll eventually get is f of xn given xn minus 1, f of xn minus 1 given x of n minus 2. You carry on till f of x1 given x naught and f of x naught, which is standalone. So here's the idea that you want to predict the behavior of a Markov process at time n. So you want to kind of characterize the Markov process behavior at time n, and all you know is, so all you need to know for that is the initial state, which is x naught. So you need to know the initial state of the Markov process, and then you also need to know the transition probabilities. That is, what is the what is the behavior of transitioning from x0 to x1. So this is like something like p10, and so on and so forth. So you just need to know the initial state and the transition probabilities. And like from an example, it might be even clearer. So let's say, so in a queuing, like in a queuing example, these things can become clearer, but all you need is initial state. That is, for a queue, the initial state is always, it's an empty queue. So n equal to 0, no elements here. At t equal to 0, we'll have kind of x0 is equal to 0. And you need the transition probabilities, right? So you have probability, like you have arrival rate as lambda and service rate as mu. So at any point in time, you can have either arrival happening or service happening. So the probability, and let's have them normalized. So let's take lambda plus mu equal to 1. So probability that you will go from any state n to n plus 1, this probability is, like, I'm just using crude notation here, this probability will be lambda. And probability that you will go from n to n minus 1, this will be mu, right? Because if you have a service, let's say you had a packet here and service is completed, so this would pop out of the queue, right? So you will go from n elements in the queue. So let's say at a certain point we have n elements in the queue. So you'll go from n to n minus 1 with a probability of mu. That is, you will have a service. And you will go from n to n plus 1 with a probability lambda, right? You'll have an arrival. So that's all you need. You need to know like the initial state of the queue. Let's say it had, like, you can take any intermediate state as well. Let's say you are starting to observe the queue and you're starting it when there are already 5 elements. And so you can kind of predict in a statistical way that, how many elements will be there in the queue at time t equal to some capital T. You can predict it because you know the way, like, the way the transition will happen. That's you just need the very minimum information, that is your initial state and the transition probabilities, that you can go to n to n plus 1 with probability lambda and to n probability mu. Like, we can study the mathematical details later, but that's kind of, actually this result is the key thing, that if you know x0 and if you know like how it can jump from x0 to x1, and xn minus 1 to xn minus 2. So that's all you need are, that is all you need to characterize Markov processes. Yeah, so like once we draw a chain diagram, it will be even like clearer, right? Is any questions? Sorry, like just kind of thought I'll do a little bit of theory before like jumping to a problem. Okay. So Markov chain, another key thing to define is a state of a Markov chain, right? State. So whatever variable you are observing, so in probability also, right, you have something known as a support set. So this is similar. So whatever variable you are observing, you have to kind of observe what possible values it can take, right? So for a Q, obviously the state will be anything from 0, 0, 1, 2 to infinity, right? Because a Q can have the empty, 1 element, 2 element till infinity, like, right? So these are the states. So states, and the entire set of states, this whole state is called this whole set is called the state space, right? And then so you have the state space, which is the the set of values that are that the Markov random variable can take, and you also have the parameter itself. So if you have your Markov process as something like x of t, so this will be a continuous time Markov. This is a continuous time Markov chain. And if you have a discrete variable, so you are kind of observing it as a discrete variable, then it will be a discrete time Markov chain. And another important factor here is discrete time Markov chain should also have a discrete state space. So a Q is an example, for example. A Q is an example of a discrete time Markov chain if you are observing it at, let's say, some sample time intervals. Like you are sampling your time into like small intervals. So at every sample, it's like this. So it is both discrete in time and also in the values that it can take, right? Now, this is an important like property. Is this clear? Okay. So, question for you is, it's kind of like also intuitive. If I give you, let's actually take an example. Let's talk about a Q over here, right? And and as I mentioned, so there is arrival rate lambda, departure rate mu, and so the values of lambda and mu are known, right? So we know that. So then, what does that mean? That we know that the probability of transitioning from n to n plus 1 is equal to lambda, and probability of transitioning from n to n minus 1 is equal to mu. Can we predict? Can we, just with this information, can we predict the expected, let's say, expected number of elements x in the queue at some random time t with just, or like, let's say we are considering discrete time, so expected value of x at any random discrete time capital N. Can we predict this based on just this much information? Or do you need something else as well?
I think we can predict using, using the initial distribution and transition probability matrix, we can able to find out.
Exactly right. So initial distribution is needed. Initial distribution or the initial state is needed. So this is missing. This hasn't been provided. So you will need both the initial distribution and the transition probabilities to predict it. Right? So again, let's do a simple example of how to depict a Markov chain, like how we do mathematically express a Markov chain. So you'll always have a state space S, let's say something like, yeah, like 0, 1, 2, right? And you will have a probability matrix, which, so it will be of the dimension 3 cross 3 cross 3. So it will be something like 2 by 5, 3 by 5, 0, and then let's say 1, 0, 0, and yeah, let me just put anything. 0, sorry, 1, 0, 0, 0, or like 1/3, 1/3, 1/3. Now, what does this mean exactly? Let's, just to understand this, we can draw a diagram, right? We have 3 states, 0, 1, and 2. 0, 1, and 2. And then we can move between these 3 states, right? So P00 is 2 by 5. So again, so what does Pij denote? Probability of the transition from state I to state J, right? So if I draw it like this, what will be the number that I'll write over here? Like I want to write the probability or the rate at which I'll move from 0 to back to 0. What will be this number here? And similarly, I'll be drawing all of these, 0 to 1, 1 to 2,
0 to 0 is 2 by 5.
Exactly. Yeah, right. So I just kind of quickly drew the Markov chain here. So 0 to 0 is 2 by 5. Similarly, 0 to 1 is 3 by 5, right? Now, 0 to 2, there's nothing, right? And then there is also something from 2 to 1, right? So 1, from 1, you only have 1 to 1. And so you really don't have these transitions, so you can just omit it. 1 to 0 doesn't exist, 1 to 2 doesn't exist. And then from 2, you have 1/3 probability of a self loop, 1/3 probability of going to 1, and 1/3 probability of going to 0. This is kind of like, I just wanted to quickly show how to draw Markov chain. So this pictorially, if somebody gives you this picture, it's very clear that from state 0, it will go back to 0 with 2 by 5. And yeah, so those kind of, that's how you depict the Markov chain, right? So, right, so is this here? And then another thing, important topic that needs to be discussed is the global balance equations. So I'll just discuss it with this example. I think that's very clear. I just cooked up the example. So yeah, I'll kind of solve it right now. Let's say somebody provides you this this chart kind of thing, and your job is to predict at steady state. And the reason we are using the term at steady state is like you don't want transient effects to be captured. You are starting, so your actual results in short term might be different, but let's say you let this process run till infinity, and you are kind of randomly picking observations at that time when things have settled into a certain kind of equilibrium. So what global balance equations dictate is, it's kind of like in chemical engineering study mass balance. So in inflow is equal to outflow, very crudely speaking. So let us pick one particular state. Let us pick the state 0. So what is the, so let's say you are initially at 0. What is the inflow into state 0? Like what is the rate at which you add elements to this, like what is the rate at which you add elements to the state 0? Clearly it is, let's so here your problem is you have to obtain probability at a steady state probability of being at the state 0. I'm denoting it as pi, probability of being in state 1, and probability of being in state 2 at time t equal to infinity. So that is why I'm not appending time here. So clearly, so let's say at state 0, the inflow will be pi 0 times p00, right? Plus pi 1 times p10 plus pi 2 times p20. This has to be equal to pi, yeah. So this is the rate at which we will have kind of an inflow into state 0, and the outflow will be pi 0 times the probability that will go out, right? So p01 plus p02. Is this clear? So we cannot have transients remaining. So whatever comes in at any time instant in a particular state, so we will have some self loops from 0 itself, some transitions from 1, some transitions to 2 into 0, and they all the original probabilities at each of these states. So we weighted by their original probabilities, pi 0, pi 1, and pi 2. This has to be equal to the rate at which we move out of the state 0, which is moving from 0 to 1 and 0 to 2. So you can write similar global balance equations at every node, right? So you have again pi 0, pi 1 times, pi 0 times p01 plus, because you're moving from 0 to 1, plus pi 1 times p11 plus pi 2 times p2 to 1, right? You're trying to find out how you can come to the state 1. So either a self loop or from 0 or from 2. And then on the right hand side, you will have pi 1, which is the probability at the state 1, times the total probability that you will move out of state 1. So that will be p1 to 0 plus p2 to 0, right? And at 2, you will write a similar equation. So again, let me just quickly write it. Pi 0 times p02 plus pi 1 times p12 plus pi 2
Can I have
times
a question?
p22. Yes.
Yeah, sorry, actually, I couldn't. I couldn't get it out. The pi 0, pi 1, pi 2. It's the probability at state 0, 1, and 2 at the time infinity. Is that the definition of pi?
Once.
Or
Yeah. Exactly. You are right. Yeah. Sorry, this will be pi 1 2, and this will be pi 2 to 1 and 2 0. Yeah, exactly. So I want to find, like at time t equal to infinity, I want to find the probability that I'll find this system in state 0 the probability that I'll find this system in state 1 and the probability that I'll find this system in state 2. Right? That will help me like, characterize the system, and I'll somewhat have an idea of what to expect. Right? Is that clear?
Okay. Yeah.
Yeah. At time t equal to infinity, I'm trying to obtain these values. So again, so that is why I'm writing these these kind of global balance equations. So again, like at 1, the total outflow, the total inflow, that is to the state 1 has to be equal to the total outflow, that is from 1 to 0 and 1 to 2. Similarly, at 2, the total inflow has to be equal to the total outflow. So we now have, so again, keep in mind that all of these quantities are known. So the transition probabilities are always known. So all of the P quantities here, the transition probabilities are known. Actually, it's right from the figure, right? Like it's known from the matrix. So this is P00, P01, etc., etc. So you can just plug in the values from this matrix and you will get 3 equations. But there are 3 unknowns, right? Pi 0, pi 1, and pi 2. But solving these 3 equations, you won't be able to. So solving these three equations, you will essentially get, let's say, pi 1 and pi 2. You will get pi 1 and pi 2 as a function of pi 0. But then, yeah, so you will get pi 1 will be something into pi 0. You just have to solve this, you will get it. You can kind of do it as an exercise. And you also need another equation, the kind of, to solve this system of equations. This will be pi 0 plus pi 1 plus pi 2. This sum of probabilities has to be equal to, like, it has to be equal to 1, right? Because the system has to exist in either of these 3 states. That is the whole state space that you have in from the question. So you can kind of try to solve this. You just plug in these values and solve these equations, and also use this constraint that pi 0 plus pi 1 plus pi 2 equal to 1. And from here you can obtain pi 0, pi 1, pi 2. You can obtain all of these 3 values individually. And so you have kind of characterized this Markov process at t equal to infinity. You can tell that, okay, this will be the probability I'll find it in this state, this state, and this state, right? So this is at steady state. This is not transient behavior, right? This is one concept that we wanted to discuss. Is this clear? Okay, so with this discussion, 2 important properties need to be discussed for Markov chains. Number 1 is transience rather. And the second property is recurrence. I'll again discuss this with a quick example so that the kind of it's very clear. And I'm again cooking this up. Right. So the first property, transience, what does it mean? It means that a particular, like a particular state will never come back to its original state. So once we reach that state, the only possibility is that we'll never come back to that state. So can somebody quickly tell which of these states is transient? We have 3 states here, A, B, and C. Which of these states will be transient? It comes from like the English word itself. It will never stay in that state. The answer is A, because if you see, the only flow from A is outwards. So you will, once you are in the state A, you will only, so there are only two possibilities. Either you go from A to B or you go from A to C. And there is no flow from B and C back to A. Once you are in B and C, you are kind of always going in circles, right? So this is how this chain is defined. So A to B, A to C exists, B to A doesn't exist, C to A doesn't exist. So this is a classic recipe for a transient state, that like you will, this state is like in steady state at time t equal to infinity, we won't have any probability. So essentially pi of A has to be 0, right? Pi of A has to be 0. Because anytime you reach A, you will eventually go to B and C. And recurrence is the opposite property. Recurrence is that you have a guarantee that any like you have a guarantee of coming back to that state, right? So let's say here in this chain, B, you start at B, you are guaranteed to transition to C. So you will go from B to C, and then again you have a guarantee that you will go from C back to B. So you are guaranteed to eventually return to its original state. So you're guaranteed to return. So this is known as recurrence. Similarly, in C, you can go from C to B and back to C, right? So you are guaranteed to return. So this property is known as recurrence, right?
Soumya,
Yeah.
I thought in transients we had the to come back to that state should be less than 1.
Yeah,
Right?
I mean, in steady state, it will go to 0.
In a
Yeah,
steady state, you
sorry.
will get to, okay, yeah.
State. But yeah, you're right. And it's basically like less than 1. So what will happen is if it's less than 1, let's say Markov process, it's any quantity less than 1, right? You have some probability p less than 1. If you keep on multiplying p, right, it will go like p to the power n. It will keep on decreasing, and if you take n to infinity, it will go to 0, right? So that's what I was saying. Yeah, you're right. Yeah, like immediately in the next step, it has to be less than 1. So that's how,
Understood.
like, you can calculate from here. Then yeah, that's kind of the logic behind it. So here, can you predict which state will be transient? Like you just have this number here. Can you predict which state will be transient and which state will be recurrent? From this probability matrix, can you predict?
All 0, 1, 2 looks like recurrent.
All
No, I
look like
think
recurrent. Can you
2 look
explain?
like 2 is transient, I believe.
Yeah. So actually, yeah, I made a mistake in drawing the diagram here. Yeah, from 2 you go to, sorry, from 1, like I use that notation. I'm denoting it as 0, 1 and 2. But yeah, from 1 you go to 0. So I actually made a mistake while drawing. Okay, right? Yeah, you are right in a way that 1 is transient, because let's see what is the probability of coming back to 1, as you were mentioning, right? It's P01 plus P21. So that's 3 by 5 plus 1 by 3. What's this value? I think I'm doing it right. 0.6. It's still less than 1, right? 0.6 plus 0.33. So 0.99, 0.93 less than 1. So yes.
Hi Sangeet, should we wait or like? Hello? In case you're speaking, your voice is not audible.
I'm really sorry. There was an issue with the Wi-Fi. Uh, um, second. Okay, I'm back. Set up. Really sorry for this. Yes, just an abrupt outage in the Wi-Fi, and I don't know why. Um, so okay, it's absolutely right. We want to check from this kind of transient probability matrix we want to check the probability of, either leaving. And so again, that by that logic, as you mentioned, that we need to see if the probability of coming back to this state is less than 1 or greater than 1, right? Because, and again, and so I was just explaining the notion of steady state. So it's very very simple to understand if you think in terms of steady state, right? Because you want to see at steady state if this state will exist or not exist, right? You really want to check that if this state is viable. And so like obviously the sum total of so there are, at any state I, you have two probabilities, right? You have the outflow, loosely speaking, probability. And as I said, I'm not a mathematician, so I'll use kind of engineering easy jargon myself, even for my own understanding. So you have a certain outflow probability, which is sum of probability ij for all j not equal to I, right? So you want to see the probability that you go out of the state I, in a way. And another probability is inflow. So you want to check, and this is for all j, including I, you want to check the probability of that you will kind of transition back into state I from any state j, right? And so for us, for this property of transience and recurrence, the key value is actually this value, right? So very clearly, actually, like I drew it wrong. You have like inflow the actual probabilities, you will also have to weight it with the original probability, right? So you pi I times Pij, maybe, right? Pij, anyway. So you want to ensure that this inflow probability is, so you're checking if it's less than 1 or greater than 1, right? So if it's less than 1, it means that if you take n to infinity, it will go to 0, right? Because it's a quantity that is less than 1. That makes sense, right? Like if you have something like even like 0.99, and by Markov chain property, you will just keep on multiplying it, right? Because it's like it's always like independent increments. We'll keep on multiplying it, and so 0.9 to the power n, it will eventually 0.99 to the power n, it will eventually go to 0. If it's greater than 1, it will go to infinity. So it will be like 1.01 whole to the power n. So this will obviously go to infinity. Just taking two examples here. So then this state will become transient, because eventually at the steady state at infinity, you won't see this anymore. The probability of this state will go to 0 as you keep on multiplying. All of these out like inflow probabilities. I mean, you do understand, right? Like, so initially you are at state I with probability, some initial probability, some probability pi or pi I, and then what will happen is this summation pji will be multiplied to the power n, and so that will be your probability pi I at 0, pi I at 0 times this will be pi I at infinity, right? That the probability that you will still be in the state I. So then, like, if this quantity is less than 1, you will multiply it infinite times, this will eventually go to 0. So at infinity, you won't see this state anymore. That is why it's transient. And the other opposite is recurrent, which is, if it's greater than 1, you can guarantee for sure that like you will see it coming back to like the state I. So it's kind of like it is bound to come back. So yeah, that is kind of the logic. So as discussed here, one obviously like the probability of coming back and like the inflow probability is less than one. So one is transient and zero. So how about zero? So this is one is transient. Let's mark it as T. How about zero? So you have P P10. This is one, and P10 and P20. You want the probability that it comes back to 0. So this will be 1 and this will be 1/3. So it's greater than 1, right? So then 0 is recurrent. And similarly, again, for 2, you can do the analysis again. P02 plus P12 is I think 0, because both of these are 0, right? So this is, yeah, this is really like this is equal to 0, and then you have a bit of P22, then that's 1/3 anyway. So this is 0 and 0. So this is again less than 1. So I think 2 is also transient, right? That's what it looks like to me. That's kind of the rough idea of how to solve these kind of problems. Any questions? Any questions, any doubts, any other doubts?
No, no,
Because
Soumya, it is very clear. The equation that you wrote below,
yeah,
pi I 0,
yeah,
it helps. Yeah,
yeah,
thank you.
yeah. So for this, like for a more like detailed discussion, should definitely refer to lecture 8 on long year. So as I said, I kind of prefer a more intuitive, way of kind of figuring out things. But I may like but like this has its pitfall. Sometimes you might end up making mistakes. So it's better if you kind of go through the more rigorous, analysis. So you will find it in lecture 8. Yeah, so all of these notions of recurrence, transient, and another important concept that I forgot to kind of highlight, which I can highlight from here, is periodicity. So here, these states B and C are periodic. You can see because you are like this will continue. This cycle will continue, right? So you'll go from B to C to B to C to B, and so on. So this, you can see that both of these states are periodic with period equal to 2, right? Because every 2 time intervals, you'll again be back to the same state. So B and C are both periodic with period 2. So this is the periodicity property. So you can kind of also check for this property in Markov chains. Like if you're guaranteed to come back to the same state, you know, if you're guaranteed to come back to the same state in a certain time interval, then it is like periodic with a period of 2. And if there is no period, like you have no such guarantee, for example, in case of A, or in general in most cases, you will not have a guarantee that you will come back to the same state. So then it will be aperiodic. So aperiodic means period equal to 1 is aperiodic. That is like it's like in a way, yeah. So by period equal to 1, what we mean is we cannot guarantee like you want to find out two different time intervals, and you are kind of tracking the times at which you arrive at the state B, right? You are tracking the times at which, like, 1 second, am I visible? Yeah. So you are tracking. I'll just draw this diagram here again, actually. A simple kind of B, C. This is 1, this is 1, this is half, this is half. So you are tracking the times at which you are in state B. So you are initially at state B at time some T1, then T2, then T3, T3. And so as discussed, so T2 minus T1 will always be equal to 2. Similarly, T3 minus T2 is also 2, and so on and so forth. So you are taking kind of the greatest common divisor of all of these time intervals, and this will come to be 2 because all of them are 2. Or even it was something like 2, 4, 8, etc. And then again, even 2, 4, 6, the greatest common divisor is 2. So then your period will be equal to 2, right? Yeah. Now for let's say A, you really will never come back. So actually, if you observe A in time T1, you will never observe it again. So your greatest common divisor, like if we don't have any GCD, we usually take GCD equal to 1, right? So this is the definition of period really. So this is period equal to 1. So A is not a periodic state. Like we won't be coming back to A at at a particular time. But B and C are periodic. And recurrent, so periodic will imply recurrent, right? Recurrent. Because if a state is periodic, we will come back to it. And we will come back to it in a certain time interval. So we are guaranteed to come back to it. So it is recurrent in a way. And the other way may not hold true. Like we can have a guarantee that we will be back to this state. We can have a guarantee, but yeah, like this, like we can have a guarantee that we'll come back to this state, but we might not have a periodicity to it, right? It might be coming back to the state at some random time intervals with a GCD of 1, but it can still be recurrent. Like in this case, this is a transient state, but like you can have examples where it is a recurrent state, right?
In the above example, how is T2 minus T1 equal to 2? I didn't get that.
Yeah. So let's say you start at B. No? 1 second. I'll just, yeah. If you start at B, like just observe the transitions here. From B, you are guaranteed to move to C, right? With probability 1. And yeah, with B, from B, you are guaranteed to move to C. From C, you are guaranteed to move back to B.
Okay, so adding.
Right? Because just see the transitions, right? From B, you'll go to C. From C, you'll come back to B. So that's, you'll keep on cycling between B and C and B and C. So if you start at B, you'll come back to B after 2 intervals. You'll come back. So this is T1, this is T2, this is T3. Does it make sense? It's always 2, right?
So if it's greater than 1, it's periodicity. If it's 1, it is, you can take it as.
aperiodic.
Aperiodic.
Yeah,
Okay.
aperiodic. Right. So, but let's say hypothetically, like in any other random Markov chain, you might not have that. This is a special kind of a case, like where guaranteed always, like you go from B to C, C to B. In some other, like, so for recurrence, you just need this kind of a like summation as the property says, right? That like yeah, your summation has to be that of pi I, like, ij has to be overall I has to be like greater than 1. But so that is all you need. Like this is a kind of a weak condition, but then it might not be periodic. Periodicity requires something more special. So so yeah, that can happen. But yeah, that's kind of the broad picture idea. But again, I'll highly recommend you, because the initial topics, like these are kind of the initial lectures. So I'd highly recommend you to like especially go through lecture 7 plus lecture 8, because this is where I thought I'll spend more time on these topics, because if these are not clear, then it might be kind of hard to follow what's to come in the course in a way. Like should have a good feel for these topics. And so long-term behavior, like classification, and then yeah, long-term behavior, both of these lectures. And so after this, like after this week's discussion, I think from the following week, in the following week's lecture, I'll try to maybe cover 2 weeks at a stretch to bring everybody up to speed with the class lecture as well. I'll see, I'll have to plan out what I want to cover. So yeah, that's the idea. If I'm able to do that, then we'll come up to speed, because these, like last week and this week, it was kind of foundation, and I didn't want to rush really. So yeah, any other questions, any other doubts? We,
You will be covering null recurrent and positive recurrent.
so again, could you repeat?
Actually, in the lecture,
Yeah.
yeah, so they have this positive recurrence and null recurrence. So I couldn't understand.
Okay. So positive recurrent is yeah. So then, so that is kind of a special like if you go beyond, like if you want to further classify recurrent, you'll have two, right? Positive and null recurrent. So positive recurrence is when you have a guarantee that you will, like, let's say T1, if I take the same notation, T1, T2, it's happening at periodic intervals. So you have a certain guarantee that, let's say, T2 minus T1 is less than infinite. So you have a guarantee that you will you will come back to the same state, within a finite interval of time. You have that guarantee that like it won't be an infinite period of time. You have to come back and within a certain fixed interval of time. Not fixed, but at least finite. In null recurrent, you don't have that guarantee. So T2 minus T1 might actually go to infinity, but you somehow have a like sorry, I should actually put expectation sign here. and expectation sign z. So this kind of is like hard to understand, that you have a guarantee that you will come back to this state, but you don't know when. Like you don't even know if you will come back within a reasonable finite interval of time. You might just, yeah, so you might have some states where like you like, yeah, you have some states where you have a guarantee of recurrence, and but you don't have a guarantee that it will be finite. So one example of positive recurrent state will be in this kind of toy example that I took. Okay, I'll just write down the values here again. So in any so positive recurrent example will be any state where, let's say, some state 0, 1, 2. So anywhere where you have a self loop with transition 1 is like, let's say I have something like half, and this is half. Just quickly hooking up an example. And then this is half. And yeah, half. Right? It's mostly covers it. I think, yeah, something like this. I just cook something up. So this state 1, right? You are kind of guaranteed that you will come back to 1, right? Once you are in the state 1, you will come back to 1. You are kind of guaranteed, and it has to be within a finite time. So this kind of a state is known as what is known as absorbing state. So whatever comes in never leaves, in a way, right? Like there is no outflow into from 1 to any other state. If you come into 1, you're just in 1. So this obviously has to be, so you will obviously, like, from 1 you will always come back to 1. So this is positive recurrent. This is just an example. Does this make sense?
Yes.
Yeah. But in general, what you will have is more like null recurrent, like whatever examples of recurrence we normally discuss, it will be like, in general, like it will be null recurrent. It is usually like, this is one particular case. Like if you see something like this, it has to be positive recurrent. But in general, we'll have null recurrence, that we have a guarantee that we'll come back to the state, but yeah, like you don't know when. Like you don't know within a finite. If it's within a finite time. So one example of null recurrent is the random walk. Which random walk follows the Brownian distribution as discussed earlier. So yeah, like you are just taking step size, like you are walking in a road. Yeah, you are walking in a road, and your step sizes and the distance that you have moved is kind of like wt plus u minus wt. The distance that you've moved is distributed as something like this. So you are kind of have some guarantee that you will eventually, take random steps here and there, and can we prove that you like eventually you will come back at some point to wherever you are currently. So here, let's say x-axis is your state space, right? You are kind of guaranteed that you will come back to wherever you are, but you don't know, like the expected time that you will come back to that same state is infinity. You don't know if you'll come back in a finite time. So yeah, that this is an example of a null recurrence. Yeah.
Yeah, thank you for your answers.
But I highly recommend that you should like quickly you should go through lecture 7 and lecture 8, especially because they have a lot of material, and it's kind of important to have an intuitive, like develop the intuition of how to work with these kind of chains before you move into like the further queuing theory stuff, that is MM1 queues and the performance characteristics and the formulas and things like that. Because yeah, like so yeah, from next class, from the next lecture onwards, I will try to go a bit faster and yeah, cover more content because the basics is already done. Yeah, I'll try to cover the like 2 weeks in the following class. Yeah, so that's it. That's it from me.
Yeah, also from lecture, can I ask a question?
Yeah.
So also from lecture 8, I gone through the lectures till continuous. I gone through it, but in lecture 8, which is the last lecture in discrete time Markov chain, the slides 31, 33, and 34, he has used some. I mean, the lecturer has used some eigenvalues and eigenvectors, and then he arrived at it. I couldn't understand those slides actually. 31, 33, and 34. He has done some problems which uses Gaussian distribution, and then he calculates using eigenvectors and values. I mean, I couldn't understand those examples.
Yeah. Okay, so actually, so like I didn't. I was primarily trying to help you. I was trying to go through the assignments and help it. But yeah, I think I can kind of maybe cover it in more detail in the like also do a short in, initial few minutes I can do on that. But the key idea is here that so initially, like again, the notion of Markov chain transition, right? So if you have like steady state probabilities, uh like in steady state, what will happen? uh yeah, just give me a second, okay? I need to, yeah, I need to just pause the video for a bit. Is my audio still there? Can you hear me?
Yeah, still there.
Okay. So okay. Yeah. So as I was mentioning, so you have your state probabilities, right? Your pi's, let's say pi, yeah, pi 0 to some pi n. So let's make this into a like a vector. I'll just use the vector notation here quickly. Pi equal to pi, let's say pi 1, pi 2, pi n, right? And so you have, and so these two vectors and matrices characterize a Markov equation, and you have P, which is P00, P01, P0n, so on and so forth, right? Pn0, Pn1, Pnn. And so what you really need to understand is, let's say the probability of going to state 1, the probability of state 1 is equal to summation of pi j pi pj to 1, right? Sorry, the probability at any state I is actually, I can use the general notation for all I, for all j, right? Because like whichever state you are, you are trying to compute the probability that you'll be back to I. So then you can write it in like in notation form as like p, like yeah, pi times the jth pji. So it will be the pi times the ith column of the matrix, right? Does that make sense? Because like row vector, column vector, if you multiply, you should just get a scalar back, right? So yeah. So
In this
this
P, can you mark which is I mean, which is I, which is I use the vertical side is I or the horizontal side? I mean,
yeah, so that kind of you can yeah, like which side? So this vertical side, right?
okay.
So then you want to find the probability that you are coming back to the state one. So you want a transition that, so this will be P10, P11, for example. So you will use this column, right? If you are talking about state one, let's say. So similarly, you can write for all I a similar equation, right? For all I. So this equation holds for all I. So you can now stack these up in rows, like you can just stack it up in a row form. So you will have, again, you will have pi will be equal to pi times. Now, if you stack it up, like if you stack pi 0, pi 1, pi 2, pi 3 to pi n, you will also be stacking these up. So all of your p0, p1 will all stack up. And so, sorry, p1, p2 will all stack up. All the columns will stack up, right? And so what is this? This is again probability matrix P, right? So then, so this is actually the steady state property that if you multiply the transition matrix to the state probabilities, you will again get back the same. So then, so this is exactly what is known as eigenvalue equation, right? In linear algebra, right? You have a times x is equal to x, or lambda times x in general, where lambda is eigenvalue, and here eigenvalue is 1. Right? Does this make sense? So this is the eigenvalue. This is eigen equation, and the eigenvalue is 1. Is this clear? So this is the property. And like I need to myself maybe look into a lecture and see the problems, but the basic concept is this. Is this clear? And you kind of have to go now somewhere. So just going to, but is it clear? Otherwise I'll just maybe go over again. But
Yeah,
you get the idea, right?
yeah.
That in steady state, like, so in like the normal way of writing this equation would be pi at state at time instant n times the transition probability matrix will give me pi at time instant n plus 1. Does that make sense?
Yeah.
Like,
Yeah. Right.
so if you take n to infinity, both of them will reduce to the steady state probabilities, right? Is this clear? If you take n to infinity, both of these will reduce to the steady state probabilities, right?
Okay. Yeah. Yeah, it's maybe correct, but yeah, I may have to think some more.
Yeah, if like at any time n, you are in you have this probability matrix, and then you have the transition matrix, and that will take you to your state at time n plus 1. And so this will hold in general for all n. But and if in limit n tends to infinity, you will take all limit here and here, so you will get pi both places, and you will eventually land up with this equation. So this has the, so you can kind of revise from linear algebra. This is the eigen equation, and your eigenvalue will be 1. Okay.
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 So actually, I gone through the continuous time Markov chain first lecture. I found it very difficult. The from first lecture onwards, understanding the
So this is
continuous time
which lecture is
from
this is lecture 9 or 11 onwards, right? Yeah, no worries. I'll like as I said,
from
like unless you
lecture
have the
9 onwards.
yeah.
Yeah.
So as I said, unless you have these fundamentals clear,
Okay.
that will be difficult. So it's like I would suggest going back, revising, and
Okay.
then moving forward, because like this is really the bedrock. Like if you understand this, you understand the rest.
Soumya, one uh, question
Yeah.
is, do you have any suggestion of the references that we can look or the problems related to recurrence, transients, hitting times, etc. for Markov chains?
Like I think the lectures itself are like uh, extremely informative. I really don't. I myself haven't come across something that is even more explanatory. So so really just the lectures themselves are really good. And professor himself has suggested some classic uh, textbooks, which you can get a hold of from your university libraries.
Got it.
And like the textbook. Hello, can you
Yeah. Yes.
still hear
Yes.
me? Okay, yeah, because there was a power outage. But yeah, so yeah, really, that is like professors' lectures are really like have a lot of information in them. It's yeah. So I myself am usually not able to retain that amount of information. So yeah, that's it.
True.
But yeah,
And
yeah.
one last query: is it possible to have the slides, because the lecture slides are very dense? I mean, I'm not sure.
Oh, these notes that I'm making. Yeah, I do. I think I did provide like a sheet, right? Which they should have shared. I'll check with the NPTEL team actually, because we do have a shared sheet with the lecture recordings and the drive links. Everything is shared. So I am updating them at my end. I'm updating them on the drive link. So I'm just doing as I've been told. And I've updated the drive link on my logging sheet. So it's an issue at there, and really, they should by now have circulated the sheet link to you. I have done my part. I have uploaded the notes to the drive folder, and I have shared the drive folder link with the NPTEL team.
We have
So
YouTube links, but not the sheet. I'm not sure.
you should also so if you're having the YouTube link, you should also have the drive link of the materials there, because I kind of log them on the same sheet.
Okay.
Uh, yeah, I log them on the same sheet, so I don't know what's. You can check with them, because I have provided both the link to my YouTube channel and also the link to a drive folder with all of the materials that I use for the week, where I've uploaded these kind of like short notes that I scribble here as well. So everything is provided from my end. I'm not sure what's going on. You can check
Understood.
with them
I'll
actually.
check. Yeah.
Yeah.
Thank you.
Okay.
Thank you.
So
Yeah.
bye.